This presentation is delivered by the Stanford Center for Professional Development.
Any questions about last time? If not, we'll continue. We're looking at the idea of left and right eigenvectors. And our next example, very important, if you go down to the pad, is a Markov chain. So in a Markov chain, the way we do it, the state is a vector. It's a column vector, and it actually is a probability distribution. It's the probability that you're in each of n states. So P of t is a column vector. Its entries are all positive or non-negative, and they add up to 1, and they represent a probability distribution. That probability distribution evolves in time by being multiplied by the state transition matrix, capital P. I warned you last time that if you see this material in, I guess, by the way, is that coming out? That is straight there. How odd. My monitor has this kind of twisted at a 5-degree angle or something like that. That's okay. So I warned you last time that if you take a course in statistics or in other areas, that this is the transpose of what you'll see there. So their matrix P will be the transpose, and they actually don't propagate column vectors, they propagate row vectors. Yes? It's what? It is tilted. Aha. Well then. Wonder if you guys can rotate your overhead camera there a little bit to make this straight. There we go. Thank you. Okay. So these matrices have the sum over columns equal to 1. So that's what this is. Every column sum is 1. And a matrix like that is called stochastic. Now you can rewrite that this way. If I put a vector in front of all ones, and that's a row vector, multiplied by p, I get this row vector here. This is the matrix way of saying that the column sums of p are all 1. Okay? So this also, if you look at it, if you like, I could put a lambda in there and say lambda is 1. This basically says that p, that the vector of all ones is a left eigenvector of p associated with eigenvalue lambda equals 1. It tells you in particular p has an eigenvalue of 1. But if it has an eigenvalue of 1, it also has a right eigenvector associated with lambda equals 1. And that means there's some non-zero vector with pv equals v. That's what it means to have a right eigenvector with eigenvalue 1. So pv is v. Some people would say that v is invariant under p. It's invariant when multiplied by p. Now it turns out that because the entries in p are positive, this is not something we're going to look at now, this eigenvector here can actually always be chosen so its entries are non-negative. And that means we can normalize it so that the sum of them is 1. Now the interpretation then is if you have pv equals v, the interpretation is just beautiful. It's an invariant distribution. It basically says if you're in the distribution given by v, that probability distribution, and you update one step in time, you will remain in the same distribution. So it's an invariant distribution. By the way, that obviously does not mean the state is invariant or anything like that. The state is jumping around. This describes the propagation of the probabilities of where the state is. And the state, it's stochastically invariant. That's what PV equals V mean. Okay. Now we'll see soon, in fact, that in most cases, no matter how you start off the Markov chain, and this depends on some properties of P, you will in fact converge to this equilibrium distribution. So that's something we'll see actually very soon. Okay. See, let's look at this idea of diagonalization. Let's suppose that you can actually choose a linearly independent set of eigenvectors for an n by n matrix A. So we're going to call those V1 through Vn. By the way, we're soon going to see this is not always possible. It is not always possible to choose an independent set of eigenvectors of A. But assuming right now it is possible, you write this just as AVI equals lambda I VI. And we'll express this set of matrix vector multiplies as we'll just concatenate everything and make it in matrix language, and it says basically A times a matrix formed, that's a square matrix formed by just concatenating the columns, is equal to V, and to multiply each of these V's by a different number, that is multiplication on the right by a diagonal matrix. So we have this equation. So you can write this way. AT equals T lambda. So there you go. 5 ASCII characters, which expresses the fact that the columns of T are eigenvectors associated with the eigenvalues lambda I. So very, very snappy notation to write this. Okay. So actually now I can explain this business. I said mysteriously earlier that you can write an eigenvector this way. And in fact, that's the way most people write it. But in fact, if you want to sort of follow this and make this work for T being a single column or something like that, you can actually write it as this. And that's, if you see somebody write that, it's for one of 2 reasons. Either they're just kind of like weird, or being perverse by writing the scalar on the right of the vector, not the left. Also, of course, this requires to interpret, this requires loose parsing. Or they're actually quite sophisticated, and they're simply writing down the scalar version of this eigenvector. I should call this the eigenvectors equation. That's AT equals T lambda. Okay. Now T, because these are independent here, T, which we haven't used yet, this matrix T is invertible because it's a bunch of it's n independent vectors. That's non-singular. It can be inverted. I multiply this equation on the left by T inverse, and I get T inverse AT is lambda. Okay? So that's the picture. This you've seen before. That is a similarity transformation, and that's a diagonal matrix. It's the eigenvalues. And in fact, so people would say the matrix A is diagonalized by a similarity transformation. And in fact, the diagonal matrix is the matrix of the diagonals are the eigenvalues. And the matrix that diagonalizes A is actually the eigenvector matrix here. So it looks like that. Okay. Now, this is just, it's really in some sense just a change of notation, but it's okay. Suppose you had any matrix T that diagonalized A by similarity. So T inverse AT is diagonal. Well, let's see, I'll call these diagonal elements, why don't I just call them lambda 1 through lambda n? And why don't I call the columns of T, V1 through Vn? If I do that, and I take this equation, I rewrite this as AT is T lambda. Now I examine these column by column, and column by column that says this. So basically, if you see an equation like T inverse AT equals lambda, or AT equals T lambda, if you see either of these equations, or these, like that, it means the same thing. They're just different ways of writing out in different matrix forms what this means. Okay? So actually, technically, these two make sense. These two make sense, even if the VI are not independent. But for this last one to make sense, obviously you have to have the VI independent. Okay? So that's the idea. Okay. So we'll say that a matrix is diagonalizable if there is a T for which T inverse AT is diagonal. And that's exactly the same as saying A has a set of linearly independent eigenvectors. So this identical. Now, sometimes you're going to hear this kind, I think it's an old word. I hope it's going away. It says that if A is not diagonalizable, it's sometimes called defective. So I don't know where or how that came about, but that's simply what it's called. You still do hear that occasionally, but otherwise it's called diagonalizable. Okay, and it's very important to quickly point out not all matrices are diagonalizable. So here's the simplest example, 0, 1, 0, 0. Characteristic polynomial is s squared. Eigenvalue, only eigenvalue is lambda equals 0. That's it. There is no other eigenvalue here. Let's try to find now 2 independent eigenvectors, each associated with eigenvalue 0. That's the only eigenvalue there is. Well, to say that you're an eigenvector of A with eigenvalue 0, that's just a long-winded way to say you're in the null space. So let's try to find vectors that satisfy 0, 1, 0, 0, v1, v2 equals 0 if you like, times v1, v2, like that. Same thing. Well, the first equation if you look at the first row, it says V2 is 0. So V2 has to be 0, so V1 is that's the only thing we have to mess with here. The second row is always satisfied. And there's no way you can pick two vectors of this form that are going to be independent. It's impossible. Okay? So here's the canonical example of an A which is not diagonalizable. Now we're going to see actually later today that this issue, it's an interesting one. It's a bit delicate. We'll get to it. It's going to turn out non-diagonalizability. Hey, that came out right. I was about halfway through that and wondering whether it was going to come out right, but I think it did. I won't attempt it again. Anyway, that property is not, it's something that it actually does come up. It actually has real implications. But in many, many cases, matrices that you encounter are diagonalizable. Not all, sadly, because that would mean a whole chunk of a bit of the class we could cut out, and which I would not only cut out, but cut out with pleasure. But sadly, can't do that. All right. So there are a couple of, we're going to see the general picture very soon, but for now we can say the following. If a matrix has distinct eigenvalues, so if the matrix if they're all different, all n eigenvalues are different, A is diagonalizable. Okay? And we'll show this later, but that's just something to know. By the way, the converse is false. You can have repeated eigenvalues but still be diagonalizable. And actually, somebody give me an example of that. What's the simplest? Just give a simple matrix with repeated eigenvalues and yet identity. There we go. So the identity in R, what's your favorite number? 7. Thank you. So that's an R 7 by 7. There we go. A very nice choice, by the way. I don't know who chose that, but good taste. Okay. R 7 by 7. So it depends how, if you count multiplicities, well, I can tell you right now the characteristic polynomial is s minus 1 to the 7th. That is the characteristic polynomial. It has, you would say, 7 eigenvalues at s equals 1. So that's about as repeated as you can get. All the eigenvalues are the same. Does I have a set? Can it be, well, I could ask stupid questions like this. Can I be diagonalizable? Can it be diagonalized? And the answer is, it already is. So you'd say, well, what would be t? You could take t equals I. So you could take as eigenvectors E1 through En. By the way, is it true that any set of n eigenvectors of I will diagonalize I or is independent? Let me I'll try the logic on you one more time. You can choose a set of 7 independent eigenvectors for I. For example, E1, E2, E3 up to E7. Now the other question is this. Suppose you pick 7 eigenvectors of I. Are they independent? No, obviously not, because I could pick E1, 2E1, 3E1, and so on, up to 7E1. There's a bunch of, they're all eigenvectors. By no means are they independent. So, okay. All right. Now we're going to connect diagonalization and left eigenvectors, and it's actually a very cool connection. So we're going to write T inverse AT equals lambda. Before, we had multiplied by T and put it over here. AT is T lambda. But in this case, we're going to write as T inverse A equals lambda T inverse. Now we're going to write this out row by row. I'm going to call the rows of T inverse W1 transpose through Wn transpose. I'm going to call those the rows. And then in this way, you can write matrix multiply as a batch operation in which you multiply the rows here by all the rows of the first thing by this matrix here. And in other words, this is nothing but this. This one is this. And now, if you simply multiply out on the left, the rows of this of the left-hand side are simply this, and the rows of the right-hand side are this, because I'm multiplying a diagonal matrix by a matrix. If you multiply a diagonal matrix on the left, it means you're actually scaling the rows of the matrix. If you multiply a diagonal matrix on the right, you're actually scaling the columns. You might ask, how do I remember that? Well, I remember that when I'm teaching 263, mostly. But then I forget. And then what I usually do is if I have to express row multiplication, I will secretly, because this is not the kind of thing you want to do in public or let anyone see you doing, I secretly sneak off to the side and I write down a 2 by 2 example to see if row multiplication is on the left or the right. And then it's on the left, I'll find out, and I'll say, I knew that. And that's how I do it. So just letting you know, that's how I know. But at least for the purpose of, while we're doing 263, I will likely remember. So, all right. So this says this. If you look at that equation, that's very simple. This says nothing more, but then these wi's are left eigenvectors, period. Now, in this case, the rows are independent. Why? Because T inverse is invertible. Its inverse is T. So the rows are independent. And this means that you have an independent set of left eigenvectors. And they're chosen. In this case, their scaling is very important. So actually, let me just review what this says. It says that if you take a linearly independent set of eigenvectors for a matrix and concatenate them column by column into a matrix, an n by n matrix, you invert that matrix and you look at the rows of the result. Those are left eigenvectors. So that's what that tells you. Those are left eigenvectors. But it's not as simple as just saying that it's any set of left eigenvectors. They're actually normalized in a very specific way. They're normalized so that Wi transpose Vj is delta Ij, right? Which is basically, this is saying T inverse times T equals I. Okay? So what you would say is, in this case, if you choose the left eigenvector, if you scale the left eigenvectors this way, they're dual bases. Now I should make a warning here, and that is that if a vector is an eigenvector, so is 3 times it, and so is 7 times it. In fact, any scalar multiple. So when you actually ask for something like left eigenvectors or something like that in some numerical computation, they have to be normalized somehow. And generally speaking, I believe this is the case, most codes, which by the way all go back to something called LAPACK, will return an eigenvector normalized in norm. In other words, it'll simply have norm 1. That's the most, if you just walk up to someone on the street and say, please normalize my eigenvector, or I'm thinking of a direction, you know, where's the direction? People will just normalize it by the 2 norm. Okay, there's other cases where they don't. I want to point out that will not produce this result. These are not normalized here. So be very careful. These are not normalized. Okay. We'll take a look and see how this comes out. This will come up soon. Okay. Now we can talk about the idea of modal form. So let's suppose A is diagonalizable by T. And from now on, you are to simply recognize this statement as saying, this is exactly the same as suppose A has an independent set of eigenvectors, V1 through Vn. If you shove them together into a matrix, I'm going to call that T. So that's what this means. Well, if you take new coordinates to be x equals T x tilde, now what this means is x tilde are the coordinates of x in the T expansion. Or if the columns of T are the V's, it's in the V's. So you would actually say x tilde gives the coordinates of x in what people would call, in this case, the modal expansion, or the eigenvector expansion. In other words, instead of writing x, which is written in the standard basis, these are the coefficients, x tilde are the mixture of V1 up through Vn that you need to construct x. That's what x tilde is. Well, this thing is x dot, and that's A, x is Tx tilde. So x tilde dot is T inverse AT. That's diagonal, and you get this. So in that new coordinate system, you get x tilde dot equals lambda x tilde. And that means that by this change of coordinate, the autonomous linear system, x dot equals AX, is decoupled. So in x dot equals AX, the way you should imagine that is a bank of integrators with a matrix A in a feedback loop. But a matrix A basically takes n inputs and produces n outputs, but it's got all these horrible cross gains. I mean, if A has all entries non-zero, It means every output depends on every input. And so you're mixing the dynamics up. That's basically what's happening. When you diagonalize like this, you have completely decoupled all the dynamics, and it looks like this. Okay? And that says that at least in this coordinate system, it's very simple. The trajectories give you n independent modes. And the modes are just simply, well, obviously, they have nothing to do with each other. They're totally decoupled. And this is called modal form. So that's a very, very common form. Now, these can be complex, in which case it's a bit weird, and you have to explain a little bit and make a story about how the real and the imaginary parts are separately solutions and all that kind of stuff. Another very common form you'll see is real modal form, and you'll see this, for example, in mechanical engineering a lot. Is real modal form, for example, for a structure. That's how they would describe the dynamics of a structure, by giving a real modal form. Now, in this case, you can, there's actually a way to construct a real matrix S so that S inverse AS is not diagonal, but it's diagonal with 1 by 1 or 2 by 2 blocks like this. Okay? So every time in T inverse AT, every entry in this, which is complex, that means for every complex eigenvalue, you'll actually collect that and its conjugate, and then actually you can take the real and imaginary part and so on, and you'll actually get a form like that. And I'm not sure. I don't remember if we've actually. Hey, we don't tell you how to construct S. That would make an excellent homework exercise, wouldn't it? Yeah. Okay. So that's the. Well, we're just going to mark that down. So find S. It's a good exercise to see if, I don't know, if any of this makes sense, and you can mess with matrices and things like that. Okay. So you get these little blocks. By the way, these little blocks like this, you should by now start recognizing. So a little block that looks like sigma n, omega n, omega n. The characteristic polynomial of this is S minus sigma n, squared, plus omega n squared, like that. Now, assuming here that omega is less than sigma, I believe that's the condition here. Oh, sorry, absolute. Nope, sorry, let me keep this out of here. The roots of this thing are going to be they're going to be sigma n plus minus square root of, and let's see, I guess it's omega n squared minus sigma n squared, something like that. Okay, so that's what it's going to look like. Now, these things are the complex eigenvalues, so that is actually negative. Otherwise, this would be two real parts and could be split. Okay. And it should kind of make sense, because this is sort of the self-exciting component between x, if this were a two-dimensional system with x1 and x2, and these are the cross components which actually give you the rotation. So this condition basically says you get enough rotation. Otherwise, it splits into two. I can tell by facial, just a quick, gross look at facial expressions. I've now confused almost everyone except possibly. Yes?
How do you, with the switching matrix, look at it and immediately see what the characteristic polynomial is?
Oh, how did I look at it and immediately say it? Well, it wasn't totally immediate, but 2 by 2, by the way, 2 by 2 matrices, that's where there are basically no excuses, right? So for 2 by 2 matrices, you should be able to work out what are the eigenvalues, what's the inverse, and things like that. Above that, no one could possibly hold you responsible for it. But 2 by 2, let's just do it. It's det Si minus A, B, C, D. I mean, this is the kind of thing you should, I guess you should know, like that. And so I did this in my head, but I sort of knew what the answer was. So you get this times minus BC. And now if I like, I could write my quadratic formula, which I don't dare do, but it would be some horrible expression. This was easier because, after all, B was equal to minus C and A was equal to D, so fewer things to keep track of. But this is what I did in principle. Okay. Now, one of these 2 by 2 blocks, which is a complex mode, they look like this, and they're really quite pretty. They are essentially cross-coupled. It's a pair of integrators cross-coupled. And by the way, if sigma is 0, you get the pure oscillation. And this is something we've seen before. In fact, that matrix is 0, omega minus omega 0. That's when sigma is 0. So you get this. You get that. And this you should recognize by now as a rotation matrix. I mean, maybe. Sorry, as it's not this is not a rotation matrix. Well, it is, but in this case, this you should recognize as a harmonic oscillator. I mean, by the way, you don't have to recognize it as a harmonic oscillator, but we talked about it, and a little bit of playing around with this would convince you that it is. So, yes? Yeah? Sorry, what's that? Here? Oh, this is not it. Thank you. This is this? Like that? Sorry, with a square? Really? Good. Great, fine. Oh, sorry. Yeah, actually, you're right, of course. This is fine. So it's sigma n plus minus j omega n. There we go. It's that? Thank you for fixing it. Good. How come no one else caught that? Well, that's one more demerit for this class. It's bad. Okay. All right. So diagonalization, it simplifies a lot of matrix expressions. So diagonalization, I'll say a few things about it. It's mostly a conceptual tool. There are a few places where it actually has some actual use. It's widely used, for example, in mechanical engineering. There, in fact, is a very famous there's very famous codes that will take a description of a mechanical thing and then spit out the modal form. So it'll list eigenvalues and it'll actually give you the eigenvectors, which in fact are these modal ones, not the complex ones, the 2x2 blocks. All right, but in fact, mostly it's a conceptual tool. And let's see why. It's going to simplify a lot of things. So if you have SI minus A inverse, that's the resolvent. Generally, I mean, if A is 2x2, no problem. You can work out what this is. If A is 3x3, this is already not a picture. No, it's nothing you don't want to see the expression for SI minus A inverse. Trust me. Okay. You can compute it easily for some particular A, but that's another story. However, we can do the following. Wherever you see A, you replace it with T lambda T inverse, like that. So we do that here, and now I'll show you a trick. This identity matrix you write as TT inverse. Okay? Now I pull a T out on the left and a T inverse out on the right in this inner matrix. I invert a triple product. That's the same as the inverse the other way around. So I get T SI minus lambda inverse T inverse. By the way, inverting a diagonal matrix, that's fine. That's easy to do. You invert the diagonals and you get this. So that's the resolvent. Okay? By the way, this is sometimes called the spectral resolution of the identity or something. There's some name for it. There's a name for this way to represent the resolvent. Actually, let me say a little bit about that. Some of you might know about the idea of residues in complex analysis. Then again, maybe none of you know about residues or partial fraction expansions. Partial fraction expansions. Come on, somebody's heard of that. Did you learn about that in some stupid signals and systems course? Is that, yes, is that where you heard about it? Okay, great. So this says the partial fraction expansion of the resolvent is this. It's really quite cool. It's, let me try to get it right. Oh, I think I can get it right. It's this, and I'm using informal syntax here. So that's the partial fraction expansion of this. Partial fraction expansion of a rational function is to write it out as a sum of terms, each of which is 1 over 1 minus a pole, s minus a pole. So that's the partial fraction expansion. Okay? The other way to do it is say that these rank 1 matrices, Vi, Wi transpose, are the residues of this function at That's the residue of this function at the pole lambda I. Okay. So the diagonalization simplifies tremendously the resolvent. It's also true for the exponential, I mean for powers. For example, if you raise a matrix to a power, if you know its eigenvectors and eigenvalues, it's very straightforward because you simply write t lambda t inverse to the k. Now when you do this, you just you line these up k times, and the t inverse here annihilates the t to the left of it. And this happens in all of these, and you get t lambda to the k t inverse. Okay? So that means it's very straightforward, in fact, to calculate powers of a matrix. And in fact, this already is a method, perhaps not, maybe not a good one, but at least conceptually, this gives you a very good way, for example, of simulating a dynamical system. Or if someone walks up to you on the street and asks, what's a to the 1 million, or 100, they're a million, what's a to the 1 million? Probably the worst thing you could do would be to write a loop that keeps multiplying an n by n matrix by a and let it run 1,000,000 times. That would be one way to do it. And the cost of that would be 10 to the 6 times n cubed if you did that loop. Okay? Now, you can also do the following. You could also calculate the eigenvectors and eigenvalues. And although I'm not going to get into the details, that can also be done in order n cubed, like 5n cubed or something like that. This doesn't matter, but I just want to make a point here. Once you calculate this and this, which costs n cubed, let's say 5, this is nothing but a bunch of calls. It costs basically 0. It costs n, which is basically dominated by the n cubed. So this can be done in 5n cubed. Okay? And the point is, that is a whole lot smaller than that. So diagonalization in this case actually gives you a very serious advantage in how to compute something. Okay? Okay. Let's look at exponential. You want to look at e to the a in general. Calculating e to the a is a pain. It's not fun unless a is 2 by 2 or has some other special structure like diagonal or something like that. It's actually quite difficult. Let's write out the power series. And if you write out the power series here, not surprisingly, when we already seen when you have a power, it's the same as simply putting the t and the t inverse here and having these things. These are all diagonal matrices, and that's nothing but this. Exponential of a diagonal matrix is exp and diag commute for a matrix exponential. You get this, like that. And that gives you a very simple way to compute the exponential. That's not quite how it's done, but it's one of the methods that can be used, is this. Okay. Now, in fact, this idea extends to any analytic function. So if you have a function which is given by a power series, that's an analytic function. You don't need to know this, but it's just kind of cool, so it doesn't hurt. So if you have an analytic function, that's a function given by a power series. It could be a rational function, could be exponential, anything else. Then it's absolutely standard to overload an analytic function to be called on n by n matrices. So f of a is given by beta 0 I, where the power series expansion of f is this. Okay? You've seen one specific example. You've seen so far the exponential. Okay? And this allows you to work out this thing. To work out this thing. So here, for example, we would have the following. We'd have f of a is t times, well, let me write it this way. Diag of f of lambda I times t inverse. There's your formula, like that. Okay, so it gives you a very quick way. This is actually something good to know about because there are a lot of times when you do see things that are polynomials of matrices, rational functions of matrices, and things like that. Those do come up a lot, and it's good to know that if you diagonalize, they will simplify. They'll simplify actually just to this single analytic function applied to the eigenvalues. Okay? So actually, I'm not quite sure why this part didn't get into the notes. That's very strange. I'll just set this over here. Okay. All right, let's look at the solution of x naught equals ax. Well, we already know what it is. It's simply this. It's x of t is the exp of ta times x of 0. That's what it is. That's the solution. And we already have a rough idea of what this looks like and things like that, or we have some idea of it anyway. Although this is not the kind of thing a person can look at right off the bat with, just take a look at a 4x4 matrix, or for that matter, a 40x40 matrix, look at it and say, oh yeah, that's going to be a rough ride in that vehicle, or something like that. Or yep, there's going to be some business cycles, I can see them. I mean, there's just no way anybody can do that. I mean, unless A is diagonal or something like that. Okay. Well, let's start with x not equals ax. T inverse at is lambda. X of t is e to the ta x of 0. That's the solution. But this thing is this. And then this has really the most beautiful interpretation. Because T inverse x of 0, I write it this way. Wi transpose x of 0, that's a number. Then it's multiplied by this thing, which actually tells you for that eigenvalue, eigenvector, whether it's this tells you whether it grows, shrinks, if it's complex, oscillates, and all that kind of stuff. And then this gives you the VI, reconstructs it. So the interpretation of this formula is really quite beautiful. And every single part can be interpreted. It's this. What happens is you take the initial state x of 0. You multiply by Wi transpose, and you get something very specific. That is the component of x of 0 in VI, in the VI expansion. So for example, if W3 transpose x of 0 is 0, that has a meaning. It says if you expand x of 0 in a V expansion, you will not have any V3. That's what this says. Okay? Because that's what this does. It decomposes it this way. In fact, let me write that down right now. X of 0 is sum Wi transpose x of 0 times Vi. That's the expansion. And that's true for any x0. Okay? This looks fancy. This comes from the fact, well, that, I mean, this is actually quite straightforward. This basically is a restatement of this. It's nothing more. Okay? So Wi transpose, which are the left eigenvectors, they decompose a state into the modal components, if you want to call the V1 and Vn the modal components. That's what this does. All right, that's fine. So that you decompose it. Then this thing time propagates that mode. That's what e to the lambda t does. It propagates the ith mode in time. Very simple formula. Well, that's the point of a mode. A mode propagates in a very simple way. It grows, it shrinks, it oscillates. That's about it. So far, by the way. And then it comes out along the direction Vi. So all the parts of this are supposed to make sense. So that's the interpretation of this. Okay, but now we can actually ask some really interesting questions and answer them. You might ask this. You have x dot equals ax. Now remember, we say by definition this system is stable. By the way, you would normally say the system x dot equals ax is stable. Sometimes, as a matter of slang, you'll hear people talk about A being stable. But it should be understood that's slang. So this system is stable provided all solutions of x dot equals ax converge to 0. They all decay. But now we're asking this. For a general A, for what initial conditions do you have x of t goes to 0 as t goes to infinity? By the way, there's one answer you can always give, no matter what A is. What's that answer? 0. If x of 0 is 0, then it stays 0, period. And therefore, it goes to 0. So the initial state, 0, no matter what A is, gives you at least one trajectory that converges to 0. I mean, converge is a little bit technical there. It is always 0, but that means it converges to 0. Okay. Now, the way to answer this is you divide the eigenvalues into those with negative real part. So let's say that's the first S of them, and the others. So these have non-negative real part. Now we can answer the question lots of different ways. One is this: you say that that's just the formula for x of t. This thing will go to 0, provided the following holds. The first S terms in here shrink. The remaining S plus 1 through n do not shrink. Therefore, this will go to 0 provided these numbers are 0 for s plus 1, s plus 2, and so on. That's one way to say it. So one way to say it is that these numbers should be 0 for s plus 1, s plus 2, up to s equals n. By the way, that is identical to saying that you're in the span of v1 through vs. Why? Because x of 0 is equal to sum wi transpose x of 0 times vi, like that. You have this. Therefore, to say that these are 0 from s plus 1 to n means that x of 0 is a linear combination of v1 through vs. Okay? So these are two different ways to say this. And there'd be all sorts of names people would call this. They would say that, they would refer, by the way, to this span. They would call that the stable eigenspace or something like that. That would be one name. Or the stable, some people would just call that the stable subspace. And the idea would be this. If you start in this subspace, the trajectory will go to 0. It might oscillate, it'll go to 0. If you're not in this subspace, you will not. So that's how that works. Okay, so that's the kind of question you can answer now. And finally, we'll handle this issue of stability of discrete time systems. So suppose a matrix is diagonalizable, and you have the linear dynamical system xt plus 1 is ax of t. Well, the solution, of course, is trivial. It's just powers of a. But if we write a as t lambda t inverse, then a to the k is this. Now, I know how powers of complex numbers, I know what powers of complex numbers do. That I can actually handle. And so you get this. Powers of complex numbers go to 0 only if their absolute value is less than 1. Right? Their imaginary part tells you about how much of a rotation in degrees you get at each step. But their magnitude tells you how the magnitude scales. And you realize that xt plus 1 is ax of t is stable if and only if the eigenvalues are less than 1 in absolute value. Okay? And it turns out this is going to be true even when a is not diagonalizable, so I don't mind stating it as a fact right now. Xt plus 1 is ax of t is stable if and only if all the eigenvalues have magnitude less than 1. Okay, so that's the condition. Actually, as in the continuous time case, there's a much more subtle statement. The spectral radius of a matrix is defined to be the maximum of the absolute values of the eigenvalues. Okay? And so one way, this is called the spectral radius, it's denoted rho. This is relatively standard notation. What this says is the discrete time autonomous system xt plus 1 is ax of t is stable if and only if the spectral radius of the dynamics matrix A, or update matrix, or whatever you want to call it, the spectral radius is less than 1. That's the condition here. All right? Now, more generally, rho of A gives you the growth or decay magnitude, asymptotic. So, for example, if rho is 1.05, in other words, there is at least one eigenvalue with a magnitude 1.05, it says that x of t will grow asymptotically. It depends on the initial condition, but it can grow as fast as 1.05 to the t. If the spectral radius is 0.7, it says that after 10 steps, roughly, the state has decayed roughly by 0.7 to the 10. That's a small number. Okay? So this is the continuous time analog of the maximum of the real part of the eigenvalues of a matrix. That's what this gives you. Okay, so enough on all that. We'll now do a bit on, maybe I'll even cover it, the Jordan canonical form. So here I actually have to ask, how many people have seen, or perhaps the right verb is been subjected to, the Jordan canonical form? So a handful of people. Did it make any sense at the time? How should we interpret this? I'd say, it did? Okay. Good. Let's look at it. So the Jordan canonical form is essentially, it's something, it's as close as you can get to a diagonalization when you can't diagonalize the matrix. So let me explain that. It's this. Any n by n matrix, any, no exceptions, can be put in something called Jordan canonical form by similarity transformation. So there's a matrix T, obviously invertible, because I'm about to refer to T inverse, for which T inverse AT is J. J, that's the Jordan form, is a block matrix. Each of these blocks, which is called a Jordan block, looks like this. It's a bunch of lambdas with ones on the super diagonal. So that's a so-called Jordan block. By the way, a 1 by 1 Jordan block is a little matrix that looks like this. Okay? So a diagonal matrix is a special case of a Jordan form. It's the special case when there are n Jordan blocks and each block is 1 by 1. So these basically have little ones in the super diagonal. We'll see what that means soon, what the ones mean. So that's a Jordan block. Now, a couple of comments about Jordan blocks. First of all, the Jordan form is upper bidiagonal. That's a name meaning it's got a diagonal and it's got one diagonal above it is non-zero. It's upper bi. In fact, it's much more than that because, in fact, there's ones in the upper. It's either 0 or 1 the upper diagonal, and not only that, it can only be 1 if the lambdas are repeated there. So diagonal is a special case of n Jordan blocks. And it's going to turn out the Jordan form is unique. Now, you have to interpret that very carefully. This is not a course on the details of the mathematics of linear algebra, so it's not like we're going to get crazy with all this. But it's important to understand what it means to say it's unique. It says that basically if two people calculate a Jordan form for a matrix, they actually can be different. One difference is simply this. They might order the blocks in a different way. However, the following is true. If two people work out a Jordan form, they have different t's here, possibly. Then there's a permutation, a block permutation, which will change one Jordan form into the other. So the way you would say this is you'd say the Jordan form is unique up to permutations of the blocks. Right? So the things people can, types of things people cannot agree on is what is J1. No one can agree on that because it depends on what you chose to put as the first Jordan block. However, no one can possibly disagree about the numbers of Jordan blocks, for example, and the sizes of them, and the sizes associated with a certain eigenvalue. So, for example, if you say, well, this has 3 eigenvalues. This eigenvalue is associated with one Jordan block of size 2 by 2. Everyone computing a Jordan decomposition will actually will agree with that. Okay. Now, I should also mention Jordan canonical form it's an interesting thing. It is almost strictly a conceptual tool. So it's used to show things, to illuminate ideas and things like that. It is actually not used in almost any numerical computations. Okay? So if you go to the web or something like that, if you go to Google and type, let's say, if you type something like, source code Jordan canonical form, you will get, actually what you'll mostly get is you'll get a bunch of harangues about how terrible it is and no one should ever compute the Jordan canonical form by numerically and so on and so forth. That's probably what you'll get. But you'll find some strange things there, but it's basically not done. Even when you do find algorithms for it, every paper will start this way. It will say, it's well known that you basically it doesn't make any sense numerically to compute the Jordan form. It goes on and it says, but let's suppose you did. You really, really had to. Then this paper is about how you might do it if you were to do it. But we don't recommend it. So that would be the kind of abstract you'd find. But not that this matters. I'm just mentioning it. Okay. So maybe it's not never, but it's awfully close. And boy, do you have to justify yourself if you actually do anything like this in any numerical application. So, all right. Now the characteristic polynomial of A is, of course, if J is block diagonal, so the characteristic polynomial of under a similarity transformation is the same. Wasn't that a homework problem? It wasn't? That's terrible. Okay. Well, similarity. Wait a minute. Oh well, that's. Maybe it shouldn't have to be. Was it one? Oh. Well, I'm glad to see though that everyone thought about that problem a long time and really. In fact, that's great because it's actually it's below even your consciousness now. It's so ingrained. It's so. It's what? Oh, the current homework. Oh, well, that would explain it. Okay, because that would have been terrible. I mean, it's a quick calculation, but the characteristic polynomial of if you under a similarity transformation, it doesn't change the eigenvalues. So the eigenvalues of A are the eigenvalues of this thing. That's a block matrix. Eigenvalues of a block matrix are the eigenvalues of all the blocks stuck together. Eigenvalues of that matrix, that's upper triangular. Eigenvalues of this matrix are lambda I with a multiplicity ni. The characteristic polynomial, in fact, of this is s minus lambda I to the ni here. That's just si minus ji. Okay, so basically, this tells you the following. If you want to get the characteristic polynomial of the matrix, you take, it's the eigenvalues associated with the blocks raised to the block size. And now we immediately see the following. Once you believe in the Jordan canonical form, which I will not show how, I will not go through the week-long proof that any matrix has a Jordan canonical form, especially because the computational algorithmic payoff is, to say dubious is putting it very, very nicely. So I won't go through that, but assuming you believe it, and you should, that is, after all, what we have mathematicians for, and they assure us that it's true. Then it says immediately that if a matrix is diagonalizable, its Jordan form must be, you can only have block sizes one by one. To say that a Jordan form has block sizes 1 by 1 says it's diagonalizable. That's basically what it says. Okay. Now, this, when you see repeated eigenvalues now, so in fact, let me explain how this works. If you see repeated eigenvalues, it means maybe you have a non-trivial Jordan form. Oh, I should mention something here. If the Jordan blocks are all 1 by 1 and this is diagonal, it's, people would call that like a, if any block is 2 by 2 or bigger, people call that a non-trivial Jordan form, meaning diagonal is just diagonalizable. So, all right, so if you see, what this says is the following. If the eigenvalues are distinct, your matrix is diagonalizable. And if someone says, yeah, what's the Jordan form? And you'd say, I just said it's diagonalizable. Okay, Jordan form is n Jordan blocks, each 1 by 1. That's the trivial Jordan form. If you see repeated eigenvalues, it does not guarantee that the Jordan, you're going to have non-trivial Jordan form. In fact, somebody quickly give me an example of a matrix that has repeated eigenvalues and yet has a trivial Jordan form. I. What size? This is very important. We talked about this earlier. 7, thank you. Yeah, okay, so 7 by 7. The 7 by 7 identity matrix has 7 absolutely equal eigenvalues. Its Jordan form is trivial, which is a pedantic way of saying it's diagonalizable. And so, on the other hand, you can have more. In fact, let's talk about 7 by 7. That's kind of big. Let's talk about like 4 by 4. Okay, so here is that's the identity. Eigenvalues all are 1. It's got 4 Jordan blocks of size 1 by 1. Okay? How about this one? Eigenvalues are all the same. The eigenvalues of that matrix are 1, 1, 1, 1, period. What's the Jordan block structure? Well, there's one block here and looks like that. So you can have a block of 2 and then 2 separate blocks of 1. Are there others for this one? Well, I could do this. I could have a block of, let's see if I can get it right. No. Yes, if I'd given myself enough room, it would have been right. How about that? That matrix. What's the block structure? What am I doing? My God. Okay, let me just get rid of that. I didn't do that. There we go. Okay, here. Since I can't even get it straight, I'll show you the blocks, okay? What about this one? what's the Jordan, I mean, the block size here you would describe as it's got 2 Jordan blocks, 1 3 by 3, 1 1 by 1. By the way, eigenvalues, this matrix, identity, all the same. Any others? What's that? 1 more 1. So we could have a single Jordan block. I don't know what I'm doing. Here we go. 1 1 1. There we go. It's a single block of size 4 by 4. And that would be the, and any others. Let's list all possible Jordan forms of a 4 by 4 matrix with 4 eigenvalues 1. There's one we missed. What is it? What is it? 2 2 by 2s. So that's exactly. So you can have this like that, and that's it. These, along with I, are the 5 possible Jordan forms for a matrix with 4 eigenvalues 1. Okay? So, of course, a natural question in your mind would be, well, let me list some. The first might be, who cares? I mean, so we'll get to that. And the second might mean, and it's related, is what's the implications? What would it mean? How would you know? How would this show up, for example, in dynamics or something like that of a system? How would you know you had one of these, and what would be any consequences of it? Okay, and we'll get to that, I promise. All right. So the connection between the eigenvalues and the Jordan blocks and sizes is a bit complicated, but it all comes from this. It says that basically if you have the characteristic polynomial is a product of s minus lambda I to the block size I. And the null space, for example, of lambda I minus a is the number of Jordan blocks with eigenvalue lambda. And we can check that because what happens is if you look at the null space, if you look at lambda I minus a, I will multiply by t inverse and t like this. And t inverse and t goes in there and annihilates itself. It's basically, that's lambda I minus j. And that is equal to a block matrix that looks like this. It's lambda minus lambda 1, lambda minus lambda 1, and then there's some minus 1s on the super diagonal, like that. And I won't draw the other blocks. Okay? Now, if you want to know what's the null space of this matrix, well, you have columns at the leading edge of each Jordan block. You have a column whose only non-zero entry, possibly non-zero entry, is lambda minus lambda I. So if lambda is equal to lambda I, you get a 0 column, and that means that matrix is going to drop rank. It is not going to be invertible. Okay? So that's what this happens. So in fact, this will happen every match at the beginning of a Jordan block. You will get a 0 column. And that says, in fact, the dimension of the null space of lambda I minus a is exactly equal to the number of Jordan blocks associated with lambda I. So over here, let's look at that. What is the dimension? Well, let's look at the null space of lambda, which is 1, minus the matrix A. And let's look in different, this is 1 times I minus A. Let's look at the different cases. And if you take I, and I ask you what's the null space of 1 times I minus A, that's the null space of 0, of the matrix, 4 by 4 matrix 0. What's the null space of the 4 by 4 matrix 0? It's what? It's R4. It's all 4 vectors. Okay, so it's 4-dimensional in this case. What is the null space of I minus A for this matrix? What is it? It's well, I wouldn't say R1 because that means that's just a set of real numbers. It's the set. It's one-dimensional, which is I think what you meant. It's one-dimensional, and it's all vectors of the form something 0 0 0. Yes, that added up. There we go. Something 0 0 0. It's one-dimensional in this case. Why? There's one Jordan block. It makes perfect sense. This case, if you take I minus this matrix, these become minus 1s, and these become 0s. And then you ask, what is the dimension of the null space of that matrix? And the answer is 2. There's 2 Jordan blocks. Same here. And in here, it's actually the dimension of the null space is 3. Okay? So basically, the amount by which the amount of rank that lambda I drops. Lambda I minus A drops when lambda is an eigenvalue. Tells you something, well actually it tells you exactly the number of Jordan blocks. That's not enough, by the way, to give you the full block structure. That comes out of lambda I minus A raised to various powers. And I'm not going to go into this, but we can, in fact, I'm not going to go into that, except that we can actually let me just ask a couple of questions here. Suppose a matrix has eigenvalues minus 1, with multiplicities minus 1, 3, and 5. 5 by 5 matrix. Let's talk about let's enumerate all possible Jordan forms for that matrix. Let's start. What are the possible Jordan forms? What's the simplest one? The trivial one, which is just diagonal. Minus 1, minus 1, minus 1, 3, 5. And if someone asked you, you know, how many Jordan blocks, what are the sizes, what would you say here? How would you describe the trivial one? It's diagonalizable here. Yeah, so you'd say, is 5 1 by 1? But you'd also say, by the way, it's pedantic to talk about Jordan blocks when a matrix is diagonalizable. So that should be the second part of your reply when someone asks you about this. Okay. Are there any others? Any other possible Jordan forms? For example, could the eigenvalue 3 correspond to a Jordan block of size 2? No, out of the question, because its multiplicity is 1. Okay? Same for 5. So these two, no matter what happens, this matrix has 2 Jordan blocks of size 1 by 1. One associated with eigenvalue 3, one with 5, period. And the only one where there's any ambiguity would be this little block of repeated ones. And what are all possible Jordan forms for 3 repeated eigenvalues of minus 1? Well, we've got 1, that's diagonal. What else? 2 and 1, and what? And 3. Okay. In this case, if I told you what the dimension of the null space of minus 1 minus I minus A is, if I told you that number, could you then uniquely determine the Jordan form of A? I'm getting this out and ready. So what do you think? You could. And the reason is the dimension of the null space of minus I minus A can be either 1, 2, or 3. If it is 3, it means A is diagonalizable, end of story. If it is 2, it means there is 1 block of size 2 by 2 and 1 of size 1 by 1. If it is 1, it says there's a single Jordan block, period. And therefore, you have determined it. Warning, that is not always the case. If I told you that a matrix is 4 by 4, has 4 eigenvalues of 1, and the dimension of the null space of 1i minus A is 2, that does not tell you the Jordan form of A. Why? Because you don't know if it is this one or this one. Each of these has 2 Jordan blocks, and you don't know which it is. Okay? So that's the idea. Okay. Let's look at well, naturally, the columns of T in T inverse AT equals J are called generalized eigenvectors. You group these according to the blocks. And these are the columns of T associated with the Jordan blocks. If you split these out as columns, then you'll get something like this. The first one comes out just the way you think it does. Or sorry, the first one comes out just the way you think it does. It's AV1 is lambda times V1. Here, that's the first one. But the next ones, because of that upper triangular, that upper diagonal, you inherit this one. Each A, Vij, is actually the previous one plus lambda times this. And so these are called generalized eigenvectors. You actually won't need to know this. They don't come up that often. But you will see this every now and then. You'll see people refer to generalized eigenvectors. Now, for if you have x dot is ax, if you put a change of coordinates, if you put it in Jordan block form, basically that splits the dynamics into, I guess, k separate independent blocks. Each one is a Jordan block. Now, you should have an overwhelming urge to draw a block diagram of a Jordan block system. And this is it. It's a chain of integrators. The chain of integrators, by the way, corresponds. That's what that upper block of one, that upper diagonal of ones is this, gives you a chain. So you should start thinking of an upper block of ones as giving you things like shift. It's a shift, or it's a chain in this case, like that, so on. And then the lambdas are simply wrapped around this way. So interestingly, people who do engineering and mathematicians both refer to sometimes Jordan blocks as Jordan chains for totally different reasons. People in engineering refer to it as a chain because it's got this chain of, it's dynamics built around a chain of integrators. And in math, it's a Jordan chain because it's a chain of subspaces. So this only shows why if you're in engineering. So that's the dynamics you see. By the way, when you see this, if you remember things like, so actually let me actually explain a little bit now, because the main thing is to get a rough idea of what on earth does it mean if you have x dot equals ax and A has a Jordan block. This says that some of the dynamics is sort of connected in, would you call that series or cascade or something like that? That's what it means. It means that some of the dynamics feeds into the other. Remember what the diagonal system looked like. It's n boxes that look like this. So the Jordan blocks are actually going to it's going to turn out it's going to have to do with dynamics blocks that cannot be decoupled. That's what it's going to be. It's going to be dynamics blocks that cannot be decoupled because they're connected in cascade, not in parallel. Okay. Now we can look at things like the resolvent and the exponential of a Jordan block. If you look at the resolvent, you see you have these this upper thing here. But if you take the inverse of that, the inverse of an upper triangular matrix is not that bad to work out. And it looks like this. Actually, it's quite interesting because now you can see something else. You can see that when you take the resolvent of a Jordan block, you're going to get powers. You're going to get s minus lambdas to negative higher powers. Didn't have that before in the resolvent. Right? So it turns out it's going to correspond to repeated poles in the resolvent are going to correspond to Jordan blocks. You can work out the Laplace transform, and this will actually at least give you part of the idea about what the meaning of these things is. When you work out the exponential of a Jordan block, it turns out, sure enough, you've got this e to the t lambda part. We're hardly surprised to see that. But now you can see what a Jordan block does. It gives you polynomials. So I think what I'll do is let me just say a little bit here. This tells you what you needed to know. When you see x dot equals ax, and let's make it simple. Let's say all of the eigenvalues are lambda, period. Okay? Now I can tell you what it means for this, what the Jordan blocks in A mean. If A is diagonalizable, the only thing you will see in the solution will be things that look like that, period. If there is a Jordan block of size 2 by 2, you will not only see exponentials, but you will see terms of this form, like that. That's only if there is a Jordan block of size 2 by 2 or larger. If there's a Jordan block of size 3 by 3, you will see not only t e to the lambda t, but t squared e to the lambda t. Another way you can turn it around and say that if you see a solution that looks like that here, That says there is a Jordan block of size k plus 1 there. Did I say that right? Yes, k plus 1. That's what it says. So Jordan blocks are basically going to be the matrix attribute, which is you are going to associate with t to the k these terms, which are a polynomial times an exponential. Okay? So, and let's actually just look at one example just for fun, and then we're going to quit. Let's look at x dot. I believe this might have come up yesterday in your section. So there, I allocated on the page enough for a 4x4. There you go. Thank you. There, it's fixed. Let's look at that. What are the eigenvalues? What on earth have I done? My God. That was a terrible, terrible crime. There we go. Okay. But you didn't violate the 8-second rule or something like that. Yeah, when you write something that stupid down, somebody should say something within, some amount of time. Okay, fine. What are the eigenvalues? 0, all 0. Okay. So just based on that, what do you expect to see in the solution when you look at x? Constants, right? And someone says, anything else? Now in this case, what do the solutions look like? The solutions here, that's a Jordan block of size a single 1. You are going to see solutions that look like this. E to the 0t, that's 1. You're also going to see t squared, and t cubed. The solutions of this x dot equals ax for this thing are going to be polynomials. Everybody cool on that? And they're polynomials of degree 3, up to degree 3. Now let's do one more thing. Let's change that so that it looks like this. Here's the block structure. What do you expect to see? Not expect. What would you see? You don't have this, and you don't have that. But you do have this. And finally, if it was just this, if it's all 0, you don't even expect, you just see constants. And of course that's correct, because x dot equals 0x. The solution is that everything is just constant. Okay? So the neural, you really want to kind of understand all of this, but the real neural connection you need to make is dynamically, Jordan blocks are these annoying terms of the form, they correspond to these. That's what they correspond. That tells you there's a Jordan block somewhere in the neighborhood. Okay, so we'll quit here.